Then we have another science highlight on modeling efforts to explain and observe trends in the upper atmosphere and ionosphere. Liang Chen.
Okay, so last week, the High Altitude Observatory at the National Center for Atmospheric Research hosted a workshop on long-term changes and trends in the upper atmosphere and ionosphere. And Stan Solomon will give some highlights from this workshop after this presentation. And this presentation is about one aspect in this particular area of research about the modeling study. And my co-authors are Stan Solomon, Ray Robo, Alan Burns, Art Richmond, Ben Foster from High Altitude Observatory, National Center for Atmospheric Research. So Robo and Dickinson in 1989 conducted a modeling study in which they doubled the concentrations of CO2 and methane, and they found that it will cause 10-degree cooling in the mesosphere, 50-degree cooling in the thermosphere. So they concluded that the global change will occur in the upper atmosphere and ionosphere, as well as in the lower atmosphere. And since this modeling study, many data have been used to detect a long-term change in the mesosphere, thermosphere, and ionosphere. In the thermosphere, long-term data satellite drag data has been used to look at the long-term change in the mass density. And in the mesosphere, many measurements such as by radar, LiDAR, and rocket sonar have been used to look at the long-term change in the temperature. And in the ionosphere, the global network of ionosphere data have been used to look at the long-term change in the ionosphere. So this figure is from Las Vega et al. 2006 science paper, which look at the long-term change in the atmosphere and ionosphere. So in the troposphere, we know that there's a global warming, but there's a global cooling in the stratosphere, in the mesosphere, and in the thermosphere. And the higher the altitude, the larger the cooling. However, in this near the mesopause region, there's an altitude region where there's essentially no change in temperature. And in the ionosphere, it is found that the electron density in the E and F1 layer has increased, and the height of the E layer has decreased. And in the F2 layer ionosphere, the trends of different sign and different magnitude have been found, which seems to be controversial. And later on, I will talk about modeling studies, which may be able to explain those different sign, different magnitude of those trends at F2 peak. And on the modeling side, different models, such as mesosphere, lower thermosphere model, the whole atmospheric model, and the thermosphere ionosphere model have been used to look at the long-term change in the atmosphere and the ionosphere. And most of these models look at the effects from the greenhouse gas, which is mainly CO2, and also look at the effects from other trace gases, such as ozone, and the effects from the long-term change in Earth's magnetic field. And these observational and modeling studies, through this observational and modeling study, consistent results have been obtained on the trends of the mesospheric temperature, thermospheric density, electron density in the E and F1 layer, and the height of the E, peak electron density in the E layer. And this pattern of long-term change supports the hypothesis of cooling and contraction due to greenhouse effect. However, some challenges remain. For example, there's those controversies that seen in the trends of the HMF2 and the NMF2 regarding their different sign and magnitude, and also the origin of these trends, whether it's due to the long-term change in the geomagnetic activity or its greenhouse effect. And also, there are some trends shows uncertainties due to limited studies. For example, the trend of the ion temperature, the trends of the wind, tides, and the wave activity in the mesopause region, And in all this area needs more observational and modeling study. So today I will talk about the modeling study with a focus on the modeling study that we have been doing at HAO, at NCA HAO. So first, I would like to give a very brief description of the NCA time GCM. Time GCM stands for thermosphere, ionosphere, mesosphere, electrodynamic general circulation model. And Ray have given some very detailed description about this, all these models. So I'll just read through real quick. So this model solves continuity, momentum, and energy equations for the coupled mesosphere, thermosphere, and ionosphere system, and for the long-term change study with a round model on the high resolution, which is a 2.5 by 2.5 degree in the longitude and the latitude. And the vertical coordinate is on the pressure surface, assuming hydrostatic equilibrium, and the resolution is a quarter of pressure scale height. And it covers the atmosphere from about 30 kilometers to 600 kilometers, and it has fully coupled thermosphere, ionosphere with neutral wind dynamos. And the input of this model is solar EUV, UV radiations, and it has imposed a magnetospheric electric field, and the tidal forcing at the lower boundary is specified by global scale wave model. And the boundary condition of the long-lived species is specified by a 2D chemical dynamic model of Garcia and Solomon. And it has very low resolution and accurate solar EUV energy deposition scheme. And the chemical heating is from Lenzak and Solomon 1992. And the radiative coolings including ozone at triple P, ozone triple P at 63 micrometer, and nitric oxide at 4.3 micrometer, CO2 at 15 micrometer, and ozone at 9.6 micrometer. And the output of the model is neutral wind, neutral temperature, major minor species density, and electron and ion temperature and density in dynamo electric field. And for the long term, we did different kinds of modeling studies. We ran the global mean version of the time GCM model, and used measured CO2 and solar activity forcing to look at the long-term change in the thermosphere mass density from 1970 to 2000 to compare with the results from satellite drag data. And we also did the 3D model simulation in which we changed the CO2 concentrations, assuming a base case and a double CO2 case, and under geomagnetic quiet conditions. And we ran the model for the different season and the different solar activity. And this slide shows the mass density trends, which is the results from the global mean model. So this is the CO2 concentration measured at the Mauna Loa Solar Observatory, and this is used as a forcing for the model. So under this forcing, this figure shows the altitude variation of the density trends in percentage per decade for these 3 decades. So at 400 kilometers, the average trend for these 3 decades is minus 1.7% per decade. And this result is consistent with the results from satellite drag data analysis, which shows the same period and the same altitude. And again, this is the average trends for these 3 decades. And if you look at different solar activities, it is found that the trend under the solar minimum conditions is larger compared to larger than the trends under solar maximum conditions. And this figure shows the corresponding change in temperature for these 3 decades. So at 400 kilometers, the temperature change is about negative 5.4 degrees. And this change in the mass density is caused by the cooling and the contraction of the atmosphere. And this cooling and the contraction happens in the thermosphere and also happens in the mesosphere and the stratosphere. So this figure shows the difference, zonal mean difference in neutral temperature between this base case and the double CO2 case. And this is a global mean. So in the mesosphere, there's about 10 degrees of cooling. And in the thermosphere, it's about 50 degrees of cooling. And in this altitude region, about 100 to 120 kilometers, there's essentially no change in temperature or it's a very small change in temperature, which is consistent with observation. And in a hydrostatic equilibrium atmosphere, this cooling will cause contraction. So this figure shows the zonal mean difference in the geopotential height, and this is a global mean. So in the mesosphere, there's about 2.5 kilometers of lowering of the pressure surface, and it's up to about 35 kilometers of lowering of this pressure surface in the upthermosphere. So we can imagine that all this cooling and contraction in the neutral atmosphere will cause some change in the ionosphere. So Richbus 1990 did a theoretical study, and the Richbus and Robo 1992 did a modeling study using TI-GCM, in which they look at the ionospheric effects of this cooling and contraction caused by change in CO2 and methane. And they found that the cooling and the contraction would lower the E and F2 layer peak altitude by about 2 kilometers and 20 kilometers respectively. And the changes of the F2 layer critical frequency will be small. And today, many studies have been conducted using the ionosonde data and also some modeling study. And from the modeling study and the observational study, consistent results have been obtained regarding the changes in the E and F1 layer. And, but for the F2 layer, trends with different sign, different magnitude for the F2 peak parameters have been obtained, and which seems to be controversial. And so we expanded on this theoretical and modeling study in an attempt to explain those different sign and different magnitude of these trends. So let's look at some results for the ionosphere. So this figure shows the change of the electron density and the height of the F2 peak between these two cases, and this is a local noon. So this dotted line is the HMF2 for the base case, and the solid line is HMF2 for the double CO2 case. So we see a lowering of this HMF2, and this is due to the thermal contraction, because in the Richbus 1998 paper, he found that the F2 peak tends to remain on the same pressure surface in the process of thermal contraction and the thermal expansion. So when there is thermal contraction, this will lower the altitude of this F2 peak. And also we notice that below F2 peak, there's a positive change of electron density, and above F2 peak, there's a negative change of the electron density. And the F2 peak itself is a small negative change of the electron density at this local time. And this figure shows the global mean results. So we see a positive change in electron density in the E and F1 layer, which is consistent with the ionosonde data. And the above F2 peak, it's a negative change. And F2 peak is right above this cross point, so it's a very small negative change in the NMF2. And we found that these trends of the F2 peak parameters also shows local time and the regional variations. This figure shows the change in HMF2 for the local noon, and this is for the 3 a.m. So we see this negative change at this local time, but also there's a local negative change and both positive change at this local time. And we know that this negative change is caused by the thermal contraction from the cooling. But this positive change is caused by dynamical forcing, which we will look at later. And also second, we notice that this change in HMF2 shows a very large latitudinal variation and longitudinal variation. And we also found that these trends of F2 peak parameters also shows solar cycle and seasonal variation. This slide shows the change in NMF2 under solar minimum condition and the solar maximum condition. So the changes under solar maximum condition is larger than the solar maximum condition. And this solar cycle dependence of the trends of NMF2 is the same as the solar cycle dependence of the trends of the mass density in the thermosphere that we mentioned earlier. And also this simulation is for the June solstice condition. So this is the summer hemisphere and this is the winter hemisphere. So the change in the winter hemisphere is larger than the summer hemisphere. And these slides explain the mechanism for this positive change in HMF2. So this is a change of HMF2 for 12 UT and solar minimum condition. And this is a corresponding change in meridional wind. So the cooling and contraction will also cause change in dynamics. So if we look at this region, there is a positive change in meridional wind. And this positive change in meridional wind will push the plasma upward along the geomagnetic field line, which will drive the F2 peak to a higher pressure surface. And this will compensate the negative change of the HMF2 due to the thermal contraction. So the net effect is a small positive change in HMF2. So far we have seen that the trends of the F2 peak parameters can be positive and negative, and their magnitude, their sign and magnitude depends on the local time, the latitude, and the longitude. So this may explain the different sign and magnitudes of these trends of these F2 peak parameters that is found in the ionosphere data. And now let's look at the changes in the electron and the ion temperatures. Zhang et al. 2005 and Holt and Zhang 2008 used incoherent scalar radar data over the Millstone Hill and looked at the change in the ion temperature for the past several decades. And they found that in the altitude region from about 350 to 400 kilometers, there's a negative change of the ion temperature in the order of 17 degrees per decade to 47 degrees per decade. And this figure shows the results from the model simulation. So first look at the change in electron temperature. We have seen that the electron temperature change in this altitude region is negative due to the cooling and the contraction. And under the condition, if there's a constant heating from the magnetosphere, then this will cause a positive change in electron temperature. And this is what we're seeing in this figure, positive change of the electron temperature in this altitude region. And this is a corresponding change in ion temperature. So below about 300 to 350 kilometers, there's a negative change in ion temperature. But and this is due to the ion and neutral coupling. And in the higher altitude, there's a positive change in ion temperature. So this should be from a coupling between the ion and the electron. And there's some discrepancies between the model and the data. The first, this negative trend in the ion temperature from model is smaller than the data. It's about 5 times smaller. And the second, there's a positive change in ion temperature from the model simulation that is not found in the data. So more observational and modeling study are needed in this area. And this slide shows the change of the MLT dynamics. There's some observational evidence that shows that the prevailing wind and the semi-diurnal tides show some long-term change in the mid-latitude and mid and high latitude in the northern hemisphere. So this is the model simulation results. This 41 degree northern hemisphere, and this is a zonal wind for the base case, and this is a zonal wind for the double CO2 case. So we see some diurnal tides here, and then at higher altitude it's semi-diurnal tides. And this figure shows a difference in the difference field. So there's a change in the zonal wind about 10 meters per second. And this is quite a large change because the wind in this altitude region is about 50, 60 meters per second. So this model simulation shows that the cooling and the contraction will cause the changes in the dynamics in the MLT region as well. And so far, we have looked at the long-term change in the upper atmosphere and ionosphere due to the change of the CO2 concentration. So now let's look at some other forcing mechanism. This figure is, shows a change in HMF2 due to the change of the geomagnetic field from 1957 to 1997. And this is a simulation done using the TIE GCM model and done by Knossen and Richmond in 2008. So this is a change in HMF2, day 80 and day 172. So this model simulation shows that there's this change in geomagnetic field will cause some regional change. In this area, it's a positive change in HMF2, and in this area, it's a negative change. And this change can be up to 20 kilometers. And beyond this region, the effect of geomagnetic field is negligible. And this is simulation results by Akhmajev et al. 2006, in which they look at the changes in temperature and the mass density in the MLT region due to the changes of the concentration of CO2, ozone, and water vapor from 1980 to 2000. So this dashed line is from the CO2 forcing alone, and this dotted line at ozone forcing, and this solid line is at water vapor forcing. So in this MLT region, the ozone forcing is comparable to the CO2 forcing, and the effect from the water vapor is relatively small and secondary. And this is a corresponding change in mass density, which shows a negative change in mass density, maximize about 100 to 110 kilometers. And this is a time GCM model simulation results, which is consistent with this model results from this modeling study. So this additional trace gas change in their concentration will cause additional cooling in the mesosphere and in the thermosphere, and some heating, warming in this altitude region. And for the mass density, it's a negative change with a maximum around 100 kilometers. So the conclusion is model simulations on trends in the upper atmosphere and the ionosphere using CO2 forcing is able to explain the overall cooling and the contraction in the upper atmosphere, as well as the resulting change in the E and F1 layer. And specifically, the model and the data from models and the data, we obtained consistent results on the thermosphere mass density trends. And this simulation shows the variability in sign and magnitude in trends of HMF2 and NMF2. And this model simulation results may explain the different sign magnitude of these trends that is shown in the ionosphere data. And the model simulation also shows the trends in the wind and the tides in the MLT region, and also smaller trends in the model of the ion temperature compared to the data, and a positive change in ion temperature at higher altitude that has not been found in the data. And the model study also shows that additional forcing, including other trace gases and Earth's magnetic field, can cause additional trends and trend variability in the upper atmosphere and ionosphere. Thanks.